Python acts as the conductor for GPU operations. It issues requests and manages control flow, but the heavy floating-point math is done by compiled native libraries launching kernels on device memory. The CPU and GPU are separate processors with distinct memory spaces. Data defaults to the CPU and must be moved to the GPU, often causing performance issues due to copying across the PCIe bus. CPUs have sophisticated cores for low-latency tasks and OS/Python. GPUs have many simpler execution units, optimized for massive parallelism, high throughput, and hiding memory latency. Software abstraction involves multiple layers: Python, framework, native backend, driver, and hardware. You are not talking directly from Python to silicon, and bottlenecks can hide in any of these layers. Tensors must reside on the same device to operate together. Mixing devices, such as a CPU tensor and a GPU tensor in an operation, will cause the script to crash. The GPU memory hierarchy includes global memory, L2 cache, shared memory, and registers. The golden rule is to maximize arithmetic intensity to hide the latency of fetching data from slow global memory. Host-to-device transfers over PCIe are slow. An optimized approach uses pinned memory to allow the GPU's DMA engine to transfer batches asynchronously, while the GPU computes the previous batch. A kernel is a compiled function executing on the GPU using SIMT. Due to launch overhead, GPUs require massive batches and predictable patterns. One massive kernel is much faster than 10,000 tiny kernels. Python is asynchronous and enqueues GPU work onto a stream before continuing. Simple time measurements often reflect launch time, not execution time. Use torch.cuda.synchronize for true timing. Calling .item.cpu or .numpy on a tensor forces a hard synchronization boundary. This halts the CPU, empties the GPU's queue, and drastically reduces throughput as it waits for all queued GPU work to finish. Kernel fusion combines multiple operations into a single kernel, drastically reducing memory traffic, eliminating launch overhead, and avoiding temporary allocations compared to a naive approach. Tiling converts global memory traffic into fast local arithmetic by loading data into shared memory. Mixed precision halves bandwidth pressure and uses specialized hardware like tensor cores for faster math. The 100% GPU utilization metric can be misleading. It only means the GPU isn't idle, but it may be memory-bound, waiting for data over the PCIe bus, not actively computing. End-to-end training follows a rhythm: data load, host-to-device copy, forward pass, autograd bookkeeping, backward pass, and optimizer step. Autograd executes a choreographed sequence of array transformations. To optimize performance, keep data resident on the GPU, batch aggressively, and leverage mixed precision. Avoid sync traps like frequent .item or .cpu calls, and use pinned memory to overlap data loading.